All right, so we are rolling, and today we try to do one of the first podcasts that we do not in Russian but in English. I used to do podcasts in Russian, so sorry for my English. It'll be difficult from time to time, but you know, it's a global world. What can you do? And today we're talking with Guillermo Restrepo, who's a researcher in Max Planck Institute for Mathematics and the Sciences in Leipzig, my colleague. And are you also affiliated with the University of Leipzig, or?
Yeah, I have an affiliation, but it's not. I'm not paid by the universities.
Okay, so we'll not mention it.
Yeah.
Yeah. So, and Guillermo is doing. So you're doing mathematics for chemistry. So I'm used to the idea that mathematics can be done for anything, mostly because mathematics need to find people who do mathematics need jobs. But but other than that, like how mathematics for chemistry works, because for a lot of people, I think chemistry is when you go into the lab and you actually mix some things. Mm-hmm. But it's not the case anymore for a long time already, I assume.
At least not in my case, yeah.
So how does it work?
Yeah, okay. Then that connection between mathematics and chemistry it has some history. Let's say I at least the field of mathematical chemistry started something like with that name, mathematical chemistry, in the 60s, 1960s, 1970s. And it was especially in those countries of the eastern part of Europe where they didn't have access to computers to do real theoretical chemistry at that time. I mean, quantum chemistry. And then they went to do theoretical chemistry with pencil and paper. And then they moved to work with graph theory and some other things.
So did I get you straight? So basically behind the Iron Curtain, people were like, we don't have resources to do experiments.
Yeah.
We don't have computers to do experiments, so we'll use pen and paper.
Yeah. And that was more or less the revival.
I can relate to that. Yeah. Okay. So and in the 60s, it was basically, and how did it work? So people tried to predict something, and then they could get resources to actually run some experiments, or
yeah.
Well, this never happened.
I think at that time in theoretical chemistry was kind of interested in trying to understand the properties of substances in terms of the molecular structure of those substances. And then those following quantum chemistry use computers and all the theoretical device of quantum chemistry. But some others said, okay, but in the drawings of chemists, where they draw molecules, that's more than a drawing. It's actually a graph, a mathematical structure. Then we can try to get something out of that. And then they did it. And they developed something like methods to extract numbers out of the molecular structure. And with those numbers, they start to create models to try to predict properties of the substances. And it worked.
So they didn't have enough money not only to do tests in the lab, but also to do the test about predictions that they made. So they made even more advanced predictions because paper was available in abundance, apparently. Yeah. Okay. But then it kind of moved away because it was clearly useful, right? So the possibility to predict the property, is it mostly useful for organic stuff because it's complex, or is it all over the board?
In principle, it can be applicable to any chemical species, but it has to do with what kind of substances we have in what we call the chemical space. I mean, the substances we know. And most of the substances, I would say more than 90% of the substances we know are from the world of organic chemistry. Then all the devices, the theoretical devices, are better suited for those molecules because they are the most popular ones.
Okay. So when you say chemical space, so people, most people, when they think about chemical space, they think about periodical table of chemical elements, and they're like, okay, that's the space. That's the space. I just combine stuff together with some other stuff. But probably you mean something else when you say that. So what's the difference? And
there are different definitions of chemical space. For instance, people started with those numbers coming out of the molecular structure. They create a space of descriptors of the molecular structure. then this is the space of molecular descriptors. Some others, for example, working in quantum chemistry, they have electronic densities and things like that as the space where molecules are located. But in our case, we are trying to say that, or our approach to the chemical space is that is made of substances which have been reported by chemists all over the history. Then if you ask me, what is the chemical space? Then I would say today is the number of substances that have been reported all over the history of chemistry until today.
Okay, so basically anything. So how does it happen? So the people synthesize some new thing, and obviously probably some chemical structures exist under some conditions, right? You need some pressure or you need some temperature. So how do you deal with that? We're talking about room temperature, room pressure, stability, or like...
That's a very good point, because it's about the substances chemists report. And all over the history, there are studies showing that several people have asked, which are the conditions in which those molecules are stable, or in which those molecules chemists have studied their behavior. And then most of the substances are very well known, but at normal conditions, 1 atmosphere temperature and 25 degrees, or at the...
You're clearly from Colombia. Yeah. With my background, 25 degrees.
That is too hot.
And 25 degrees in St. Petersburg. Whoa.
No, but sometimes...
This is a very, very good day, sir.
No, but sometimes you also need you also consider the temperature where the substance is dissolved. For example, 100 degrees for water if you are treating the substance in water, or some other solvent. Then it depends on the boiling temperature of the solvent. But the range of temperatures and pressures is very narrow. But now there is a new trend in chemistry, which is extreme conditions. Then now we can play with different conditions, and we see what's the behavior of those substances under those conditions. For instance, if you ask me what is the chemical formula of table salt, then I would say NaCl.
Yeah.
But that may change. I would need to say, okay, but under which conditions? Then, for example, at the inner core of our planet, it's something like Na3Cl7 or something like that.
Oh, so because it's super high pressure and a lot of temperature, the molecular structure is different, and like you can get more potassium and more chloride in one molecule?
Yeah, it's something like the first helium compound.
Okay.
It was made under it was by a Russian. It was made by very strong pressure. But as soon as
sounds like our cultural predisposition to put something under very hard pressure and then see if it blows up or something. But my question is, you mentioned quantum chemistry, for example, for a long time, and we had several discussions, and that's very interesting, the quantum computing area. And for quantum computers, you need to cool them down really low temperatures, like 4 Kelvin or something like that. And my question was more into this direction, because probably you need certain materials that are good for these temperatures, and some of those compounds might be very different from the ones that we have here. So that's also the case, right? So you use theoretical chemistry for that.
Yeah. There is a lot of theoretical chemistry in that direction, and they are interested in particular in the electrons and in the conductivity of those materials, for example, superconductors and things like that. And then you need to go down with the temperature. Yeah, but most of the substances have been treated at normal conditions.
But you can predict some properties of the substance if you change the conditions. This is also something within the scope or not?
No, with that, those things that I mentioned with paper and pencil are normally for substances under normal conditions. And you need to go...
Why is it so hard to...
Because I think it's because of the vast amount of chemical knowledge we have is at those conditions. If we were under extreme pressure, for sure we will have more knowledge about those conditions, and this would be our challenge. What happened with substances at 1 atmosphere pressure and 25 degrees in Colombia.
So if people did chemistry on Venus, then they would have a totally different chemistry.
Accustomed to that, yeah.
Okay, that's interesting. Okay, so that's history. But like, what are you guys doing now? What is the current state of this theoretical chemistry? mathematical chemistry.
Mathematical chemistry. I think most of the people working on mathematical chemistry are working on devising more and more descriptors of those drawings, of those molecular structures.
But is it the drawing representation actually correct because of the quantum things there and so on?
If you ask a quantum chemist, he's going to say, no. That's
if I ask you, you say it's
that's
fine.
totally wrong. But I think it's something like at the coarse graining level of abstraction you need to get. Of course, at the most fundamental level, you need to go to the electrons and you need to pay attention to where the nuclei are located and things like that. But that's for some particular aim, for example, for superconductors or things like that. But if you are interested in, for instance, the interaction of a small molecule with a protein, you don't need to go perhaps to that level. And perhaps at that level, the drawing is enough. And that's the level of abstraction where chemistry normally is living. And then perhaps it depends on what you want to achieve. But I think for most of the chemistry, that level of drawing or treating molecular structures as those drawings is fairly good.
So you basically study the graph properties of the molecules and then you predict the new properties, or do you predict the new molecules as well? Like, is it also part of the mathematical chemistry or not?
Normally what is done is you have this molecular structure, you have the drawing, the molecule, and you extract with different algorithms. You extract numbers out of the molecular structure, and then you try to develop models to try to predict some properties. But it's to try to predict the property of the substance. Is not going in the direction of trying to predict a new substances. But now with those with the advent of machine learning and artificial intelligence, that's the direction has changed, and now people are working with that.
So let's decompose it into two things then. So predicting the properties, like the idea is that chemist discovers a substance and you don't know where to use it, and so you can get insights on, okay, this might work for this receptor in pharmacology, or I don't know, this thing can form crystals, so we can use it, I don't know, for some material. So how does this thing work regarding the properties? What is the motivation to get the property? Because usually chemists, my impression is that probably, I'm not sure. If you're a chemist, come to the podcast and explain. If you're experimental chemist. But my feeling is that you have a task, you need to design certain compound for certain problem. No?
That's not really.
Okay.
Sometimes you say, I want to...
Ignorant computer
scientist.
Normally
when you apply for grants, you say that. You say, I need to cure breast cancer. And then I think this molecule or this family of molecules are the most important one to treat breast cancer. And then you apply for the money, you get the money, and then you try to do it. But there is no procedure telling you that is going to work. There are some heuristics and things like that. But normally there is a philosopher of chemistry telling that chemistry is something like the aim of chemistry is discovering substances. If they work, good. If they don't, at least we expanded the chemical space. That's more or less the way of working in chemistry. But it's not that you need to solve that problem and then you try to synthesize the molecule.
But why do you predict properties then? My question was originally, why do you predict properties, right? So if it's just a substance discovery, then prediction of the properties doesn't
absolutely.
fit into this paradigm,
it's
right?
because you are interested in the properties, but it's not always the aim of chemistry. It's something like a dream in chemistry, but it's not the real way of advancing chemistry.
Okay. So some people just do discovery, and then some other people try to find out whether certain substance works for certain application, and their mathematical chemistry can help, for example.
Yeah.
Okay. And regarding the second part, so regarding the machine learning part, that I know at least something about. So how does machine learning change this substance discovery issue? Well, what's going on there?
I think in terms of speed, in terms of, for example, there is a paper telling that reaction times are something like they are multiples of our daily life times. Then, for example, 24 hours reaction, 12-hour reactions, And it depends on how much time you take to take your lunch, or how much time you go to sleep, or something like that. Those are the times, the typical times in reactions. But now because now those machine learning or artificial intelligence approaches are coupled with robotics, and they don't sleep. then the speed.
Oh, so you were telling that there is some empirical evidence that the substances that we discover are connected with the fact that we are humans.
Yeah, there is anthropogenic bias here in the expansion of the chemical space. Yeah.
Wow, this is fascinating. So because like if basically if a different species knew how to do chemistry, they would find different substances, probably, or we are not sure, but there is a chance. Like if ants were intelligent and they found chemistry, they would have different experiments and thus different.
They would put their vessels in a different time or for different reaction times or something like that. I'm pretty sure about that. Yeah.
Wow.
That's chemistry. Chemistry is very social.
Okay, but like the point is, so when we can do algorithms and combine them with robots, we basically can run automated experiments that humans didn't run before. So does it mean that we'll see a lot of new compounds in the coming years, or what is the expectation here?
Could be, but it depends on the training set you have. And that has been a lot of there is a lot of discussion about that. For example, we have run a study where we tried to explore the diversity of the chemical space all over the history of chemistry, all over, not from 1800 until 2015. We published a study, and then we found that most of the substances we have discovered have been or belong to organic chemistry. And then with that setting, with that powerful amount of organic substances, then you have a strong bias. And the bias is that most of the chemistry is done in that direction. And then if you have a biased chemical space, and that's your training set,
this is where you go. You keep on going in this
direction. And then
you
keep on going. Then you have a self-reinforcing process. And then you discover something, but it's something expected.
Okay.
Then I recently wrote something, and is that if you really want to go out of the box, then what you need to do is to allow those algorithms, and coupled with robotics, to try to change those conditions, to try to diversify what we already know. And in that sense, we can take a lot of advantage of those technologies to see to get a richer panorama of the chemical space.
But how would you avoid this bias? What would be a natural way to do it? Like, I had an idea that one of the options would actually be to send them to Venus, for example, because then you end up in a different condition.
But you can do that here. You can change the conditions here.
Yeah, just put them under pressure or in vacuum or colder, hotter, and so you shift away from this.
Yeah, and there is another point here, is that chemistry, and perhaps most of the sciences, and especially the experimental sciences as chemistry, they report the positive results.
Yeah, okay.
Then we don't have records of failed reactions, that they are called like that. And is that you try this you try substance A with substance B, and then you hit that and you don't get any result. You keep having A and B, then you don't report that. But that's important. It's important because that can be used for your training set. Then the idea is to report everything that you do. And now there are also technologies where you put, for example, an electronic device in the reaction vessel, and then this device is collecting a lot of data of what is happening there inside, and then you.
So you want to get rid of the, how do you say it, publication bias, basically.
Publication bias, and also of that dream of perfection that every chemist report the synthesis of a new substance, but he has tried or she has tried 100 other reactions that they don't go to anywhere. Then
why is it so? Like, it seems to be something that you can definitely put in the appendix, saying just, hey, by the way, this whole things didn't work.
That has to do with the language, with the ways of communicating in chemistry, and I think that has to do with the connection with industry. They are interested in positive results, but they don't.
No, but like my point is that if you got a positive result, but you also got a lot of negatives on the way, you can still report them.
No, journals are, before some 10 or 20 years ago, they were not interested in that. Do you report that in your notebook, but not for the public?
But yeah. Okay.
But now there is a strong push to try to get those failed reactions openly available.
Because we actually had so I had a paper with two of my students, and we basically made a paper on negative results. And in NLP now there is a workshop on negative results in NLP, specifically only for negative results, which is amazing. I think it's a very cool initiative, and shout out to people who do it. And we reported like we did this and this and this and this stuff doesn't work, and we, of course, I put a link to archive once we release the preprint, and I don't have huge following on Twitter, but some machine learners follow me, and so somebody reposted it, and then like 4 or 5 people came into this Twitter thread saying, "Oh, we had the same thing like 2 years ago or something, but we didn't publish it because we thought that we did something wrong. We thought that something didn't work because we made a mistake." And it means that like it hinders the progress, because also I'm pretty sure that next time now, if the person decides to Google some papers on the topic, they'll find our paper, and at least maybe they'll get discouraged a bit. They'll be like, okay, maybe this doesn't sound like such a good idea. So it helps to speed things up. And so in chemistry, it's the same.
Exactly the same. For example, if your PhD student is trying to synthesize a molecule, and if he tries to do something that has been done for, I don't know, hundreds of times but not reported, he could save time. Sure.
Okay, so coming back to property predictions and new substance predictions. So you say that we are biased by history, but generally you seem to deal a lot with history of chemistry, right? So you have several papers on history of chemistry. So why do we need to know history of chemistry? What's the point? Well, some people would advocate that we don't need to know history at all. Why?
No.
Not even to say history of chemistry.
Yeah, Tolstoy wouldn't say that.
Okay, Some wouldn't, but still.
Yeah, no, I think it's very important to know history, but not because of the details of who said this or who started this field or something like that, but because of the large-scale patterns.
Okay,
that's where Tolstoy was very interested in that. Then that's what I think is, for example, in history of science, there is a new trend to try to detect those large-scale patterns. And for example, in the evolution of chemistry, and in particular of the chemical space, we found that if you count the number of substances reported every year, you collect all the substances reported every year in scientific journals, then we counted that. We have access to one database with that information. And then from 1800 until 2015, we counted that. And then we found that there is an exponential trend. And is that the variability was very high at the beginning, but with the passage of time, it's dropping and dropping and dropping. And I think that's telling us something about the self-reinforcing processes in chemistry. Something like the variability is going down because we know we are repeating ourselves. And we found that even with the world wars, with the introduction of new theories, the growth rate has been stable for more than 200 years. And I think that's important, because if you have that, then you can try to do forecasting. That would be also nice.
And then, well, even exponential things, despite the fact that exponential things are notoriously hard to forecast. But like if...
but
because at some point probably you can hit, because we have this growth. Yeah, it may be exponential, but it might be a sigmoid, right? So what to do about that? There is an economics paper, a beautiful one, that basically says that return of investment of science is declining. Throughout history. It's a similar approach, but now applied to science at large.
I think we can keep expanding the chemical space in an exponential fashion if we can keep having the amount of chemists or more robotic stuff to keep expanding the space, because the possibilities for the chemical space are very huge. I think we are but very, very far from completeness. Can you imagine the possible combinatorial ways of combining 100 elements? We have 18 elements, but really accessible in chemical terms, we have about 100. We have a lot of possibilities, and we have just explored a small part of that. Then I think it's not a problem to keep thinking that it's possible to maintain the exponential growth, but we need the people or the technology to support that, and that's a problem with the economics.
No, but like exponential growth, generally, everybody in business loves exponential growth because it's like, whoa, it's high return on investment and so on. But then we come back to the properties thing. So just discovering things that are not solving some practical problems is something that probably people are not happy with. So
yeah.
But how close are we to the situation when you can actually kind of submit a molecule to some software, probably and then the software would get you some probabilities of some kind of matching between the substance and potential applications? Like, do we have something that is already, or are we going like Google for chemical reactions? You know, like you take a substance, you rather not even just Google for chemical properties, like you drop a substance and it just gives you what are potential applications of the substance throughout.
No, I haven't seen that. What I've seen is that there are kind of things like that, but very tailored. I mean, you put
because this is something probably that big pharma would be super interested in, right?
And that's they normally have that. Then you have the library of substances, and then they put off those substances for one particular protein pocket.
Okay,
but that's a very narrow field of applications. Perhaps what you have here is the new molecule saving hundreds of lives for another protein, or even if you combine that with an inorganic substance, you have something totally different. But that's very normally those Google things are very, very narrow for particular applications. Yeah.
But do you think that this will change as we progress, or is it still far away? Because it feels that there are a lot of applied problems. Like, I think what we learned in the past several years is that, first of all, people don't know nothing about medicine. Second of all, we know way more about medicine than we think we we do, because like we managed to create vaccines really fast through genetic engineering and so on and so on. So there is a clear mismatch between the knowledge of people about biology and medicine, and chemistry is a natural part of this, and what some cutting edge technologies can do in this space. And partly my experience with, for example, machine learning is that once this thing happens, then people who don't understand how this works and why it is useful, they basically start to say, I don't want to pay my taxes to support this thing. You know, I don't want people to research it further because I don't see any use in it. So how do people in this chemical and biological space deal with this thing, or mostly organic chemistry?
Yeah, that has been a very, very difficult issue for chemistry. But I think now for example, with machine learning and those technologies, perhaps that could contribute to that, because you can, first of all, you can try, and there are several high throughput screening methods in chemistry. You have a very small amount of the substance, and then you run different biological tests.
This sounds like Elizabeth Holmes.
Yeah.
Be careful.
but you can get all those tests for different pathologies, for example, and then you record that information. And if you have a very large database of those substances with those properties that you can record very fast, then you can then apply those machine learning technologies to try to see, or to try to learn something. But of course, the problem is always the bias of the.
Okay. You also, so another fascinating paper of yours that I came across was about periodic table and how it developed throughout history, that it's a relatively new concept, and people try to rebuild it and redesign it. It would be nice if you just explained why is it important to organize it in a table? Why is it a game changer? Or maybe it is not, I'm not sure. And the second thing in this paper, you also mentioned in particular that you studied how people worked with periodic table for the last 200 years. And there is some impact of wars on this historic process. So if you can
I think
tell about that would be interesting.
I think when Meyer and Mendeleev started to work on the periodic system, what they did was to kind of collect the chemical knowledge they had, and that was based on the chemical space, the substances they knew at that time, and they started to find patterns. This element is similar to this one because it forms a similar compound.
Like carbon and silicon, for example.
Yeah, for example. They started to do that. And then what I was thinking when reading these famous authors then was that connection between the substances and the periodic system. And the periodic system is, for example, in the case of Mendeleev, it was something like he wanted to teach chemistry in a very systematic way, and that's the word system. Mm-hmm. And then he came across with the idea of the periodic system, but it was something like the periodic system is able to condense most of the features of the chemical space. Mm-hmm. But then you need the chemical space. I mean, you need substances, and it's something like the chemical space is the periodic system is an statistics of the chemical space. Then this is an important point. If you change the chemical space, then perhaps you change the periodic system.
Yeah, okay.
That was our question. What happened? We have records of the chemical space year after year. Then what we did was to build up a periodic system for every particular year based on the knowledge we have of the chemical space. And what we found, we have two papers on that. One was...
And you also tried to characterize it, like how different it is from year to year.
We measured something like a distance between every couple of periodic systems. And then we found that between 1800 and 1869, and that was the year of publication of Mendeleev periodic system, we found that some of the... I would say that more than 90% of the structure of the periodic system was recovered by that chemical space. And we recently ran the study between 1800 and 2021. And what we found is that the chemical space is evolving, and I mentioned before that is in a biased way, full of organic chemistry, and is converging. The periodic system, the chemical space is expanding exponentially, but the periodic system is converging. It's something like self-reinforced.
It's like it's staying the same. But wouldn't it mean that this is the representation of the bias too?
Yeah, for example, yeah. I think if we had bias...
So it's not necessarily that it's correct. It's just we do chemistry around it.
I think it's not a scientific truth. It's something like... It's the product of the chemistry we do. That's what happened. If we do more inorganic chemistry, we would have another periodic system, I'm pretty sure.
Okay.
And what you said about the effect of words, and we found that, for instance,
you published it. I just
but you mentioned that a couple of seconds ago. Then we found that the Second World War, with all the research that was done on actinoids and lanthanoids, actinoid was discovered or were synthesized at that time. Fluorine chemistry had something like a revival because in all that research of actinoids, they needed some very stable materials to be able to store those very reactive substances. So they were basically developing nuclear weapons, and for that they studied a lot of the areas. And the most affected chemistry of a particular element was fluorine, because that element was providing materials able to store those very reactive substances. And then it was because of the Second World War. Mm-hmm. It was after that the chemistry of fluorine skyrocketed. And then it also changed one of the patterns in the periodic system. The periodic system is converging, but you see instances, clear instances.
What kind of pattern? Like it's...
for instance, at the beginning, if you ask me, there is a lot of discussion on the position of hydrogen on the periodic system. For example, Mendeleev also had trouble to locate hydrogen.
Yeah, okay.
And Meyer too. Then, if you ask me where is the position of hydrogen, I would say it depends. If we have the chemical space of the first half of the 19th century, hydrogen should go to the alkali metals, because the chemistry of hydrogen at that time was similar to the chemistry of the alkali metals.
Okay.
But now, with the explosion of organic chemistry, hydrogen is more similar to the halogens. Then it jumped from the first group to the group of the halogens and in the other corner of the periodic system. That's a clear evidence of how our way of
but
expanding.
it's still represented. I think in the textbooks, maybe I had old textbooks, but in the textbooks it's still number one. So
because
what are you doing? You're demoting hydrogen to a lower position.
I would say that I
Guillermo.
would put it in the middle, and you decide where to.
This is the
hydrogen-
most abandoned element in the universe, and you're doing this to it. Come on.
yeah.
How can you?
Yeah, poor hydrogen.
Yes, this is unbearable.
Yeah,
but
yeah,
like
yeah.
the point is that the system is kind of summary of all the knowledge we have about chemistry, and so if the knowledge about chemistry changes, the system
Is
kind of-
affected.
yeah, okay. And if we come back to the situation with robotized experiments and automated experiments, does that mean that, like, do we condition these experiments on the current state of the periodic table, or don't we? Like, how does it have an impact?
No, I think chemists don't pay much attention to.
Because I think that one of the things about the bias, it would be interesting to investigate whether the bias of chemistry is the product of periodic system, right? Because once you get such thing that then and you combine it with mass education in schools, you reinforce the chemistry bias super hard.
That's true, and we have found evidence of that. For example,
Okay.
but I think when the periodic system was formulated, there was enough knowledge of the chemical space from the inorganic side, and organic chemistry was blossoming. Then it was something like a good sample of a good sampling of the chemical space at that time, in the 1860s. And now about the something like whether we are exploring the chemical space because of the periodic system. We have found evidence of that.
Whether the convergence, you mentioned that it also converges.
Yeah, but I think it's not because of that. I think it was because it's by far much easier to do organic chemistry because we have more material to do that, and the theories we have developed are more suited for organic chemistry.
Also, we happen to be organic, so we believe that.
Yeah.
Okay.
Then I think it's easier for us to go in that direction. But now when it comes to explore, for example, the chemistry of a new element, then you say, okay, let me see. This new element has this number of protons. And with this number of protons, I go to this place in the periodic system. Then it belongs to the group number, 13. Then, because of its belonging to that group, then you start to explore the chemistry of it as if it were similar to those elements.
And you look at the other substances you have that are
but then
kind of
now
similar.
you have the bias because of the periodic system for
Okay.
those new elements. But before the periodic system was formulated, nobody knew about those locations of elements in those groups.
But when they formulated the system, they also predicted some elements they didn't know existed, right? Mm-hmm. So it does have some predictive power in a sense that it allows you to predict some, not even substances, but atoms.
Yeah,
that were not
there.
So,
That's
okay.
that was the power of, and I think.
But is it the case that, like, because you're saying that the periodic system is the function of our knowledge of chemistry, is it the case that there are some structures that we don't know because we have this periodic system that we didn't experiment with, like regarding the completeness of our chemical knowledge of inorganic chemistry?
Yeah, I think that's related to the conditions of the chemical substances. I think we have the periodic system we have. Then
because also periodic system is connected with the physics of these things, right? So on the atomic level, you just have so many protons in the nucleus, and then corresponding number of electrons, and then you can say, okay, maybe there's heavy oxygen, and maybe the chemistry of heavy oxygen would be different as the chemistry of normal oxygen. But does it mean that heavy oxygen is a different element or not with regard to its chemistry? This is something that we actually don't know, or we just assume that it's... How do we do that?
There are theories about that. For example, quantum chemistry, or for example, quantum chemistry now adding and relativistic effects is very powerful for heavy elements. For example, it works pretty well. For example, with that,
and you basically want to do it if you want to do some nuclear power, next gen nuclear power,
or if you want to understand the chemistry of a new gold material or something that. Or normally that's a very, very important field of work nowadays, because those elements are are using the technologies we are using right now. Those,
oh, really?
Yeah.
So
lanthanides,
how
actinides.
much radioactive elements do we have?
Oh,
in this
yeah.
room?
For example, many of the possibilities that you have in your cell phones is because you have lanthanides there. And
okay.
then for that, to understand the chemistry of them, you need relativistic effects.
Okay.
Quantum chemistry at the level of electrons. Yeah. That's what you need.
Yeah. When you look at what is the current level of technology for the microchips, and it's like several nanometers, which is less than the size of an atom. You're like,
Yeah. Also,
some stuff that happens there is
exactly.
Okay. I see.
Yeah.
All right. So how do we deal with this completeness, generally speaking? Because at some point you mentioned that we are very far from completeness. But how do we even know how far we are from completeness?
You can do some counting, and you can count how many atoms, or how many atoms, considering all the possible elements, are in the universe, and I think it's 10 to the power of 76. And with that, you can play some combinatorics, and then you see that the amount of possibilities is very huge. For example, Weiniger, one cheminformatician in the 90s, he said that, okay, the chemical space is very huge, the possibilities, the combinatorics you have there is very huge, but that's mathematics. But you need to go to the level of chemistry. You need to say, okay, those substances that you are talking in or telling in mathematical terms, they are only very few of them are really stable at our conditions. Then he said that he had the belief that there are more or less 10 to the power of 200 or something like that, 10 to the power of 200 molecules available for us.
That might exist.
Yeah, available for us. And then even for that small number, we are very, very, very far from getting there. Because
okay, so 10 to the power of 200, this would mean 200 zeros after 1. A little bit hard to imagine.
I think that's
a bit on a difficult side.
I was counting, and you cannot even label those substances and store them in the universe.
Yeah, of course, because you have less atoms. Of course,
and there is a limit for that. The Bekenstein, he published a paper in the 80s where he said the amount of information you can store in the physical universe. And the chemical space is bigger than that.
So we never reach completeness in any
not even I think, I don't know.
This is actually an intriguing question. Then that means that we kind of have to navigate. So our path determines what substances will we discover as we go through the chemical space. And since our capabilities are limited, if we want to reach to a certain position in the chemical space that far from where we are now, we kind of should not fuck around. We should go in this direction.
Yeah,
very
exactly.
Precisely.
That's that I have written about that.
Sorry for my French.
You need to be.
I'm not sure if this podcast is supposed to be clean or not, but I was so amazed with 200 zeros that I didn't know what to do about it. So.
No, you need to be very clever in which regions of the chemical space you are going to explore. And that justify all the methods chemists have devised to try to get to particular spots of the chemical space.
Okay, so I have a question for you. What gets us Dyson sphere? So this Dyson sphere is this idea. So there was this guy who was basically trying to describe different civilizations, stages of development in space, I think. And he had this idea that at first you basically harness the resources of your habitat, then you harness the resources of your planet, then of your solar system, and then of the galaxy. And so for the solar system, the idea is that the most energy you can get out of the solar system is to build a sphere around your sun and to absorb all the energy of the sun and then reuse it for your own purposes. Mm-hmm. So it seems like a logical way to go. So which chemistry do we need to develop?
To go in that direction?
Yeah, to go in that direction.
Then we would need to explore the chemistry of substances under those particular conditions.
Okay. So it's vacuum and close to higher temperatures.
Yeah,
and stuff like that.
And there are several papers on that, and also on theoretical approaches to try to understand that, because you need also to modify your theoretical devices, because normally they are suited for ambient conditions. but then you need to move forward.
And like another question would be probably for the space lift. Like, what is the chemistry we need to be able to construct space lift, to be able to raise stuff on the orbit through some actual mechanical labor rather than.
Yeah, then you need to go to the level of properties, and that's where it's important to study also the properties. But no, I don't know.
Because that also seems important if you want to be transplanetary species, you need to be able to deliver stuff in space cheap.
Yeah.
Like at some point, I remember I was talking to a guy who was doing nanomaterials and this nanotubes, and he was claiming that they're very, very how do you say, very allow you to build very, very robust constructions that are very light. So he was very excited about them because he was thinking that he can build space lift with it, but. Somehow,
those new materials are changing many of the things we use now.
Okay, so another civilizational challenge in chemistry. So you have a paper on which refrigerants should we use, which is beautiful. So if you consider, this is something they don't write in IKEA. You know, you go to buy a new fridge and they don't reference you. You should talk to them because I would like to know now. Now that I read your paper, I'm like, okay, is this thing good for the world or not?
Yeah.
So can you tell about that?
Yeah, the point in that paper, I think what we were trying to do was to convince the community of environmentalists that if you have a problem which is characterized by several properties, for example, the case of the refrigerants. At that time, we were worried about the environmental properties of them. Then, for example, I think we use global warming potential ozone.
Is this idea that Freon was creating holes in the ozone layer?
That's called the ozone depletion potential, and that you can measure that you can take the substance and you measure that, and then you get a number.
By the way, nobody's talking about that anymore. Did we solve the problem?
No, because it's kind of solved.
Okay.
Yeah, cool. They stopped the production of that, and that was more or less the idea of refrigerant. They said, okay, this substance, this beautiful substance, is changing a lot of our stratosphere. Then they stopped producing that substance and they look for replacement. In that paper, we were exploring because they changed the refrigerant, they replaced the refrigerant for another one, working under better conditions in refrigerators, but the question was: is good in terms of environment, in terms of and then we were collecting properties of ozone depletion potential and the different environmental properties, and we found that no, they are not doing that well. They are good for the companies and for the refrigerator, but not for the environment. And that paper was...
And what was the reason for it? Because they probably switched to a different substance because they had some science on their hands that they claimed that it's better. Is it they use different assumptions than you did? Or like what was the nature of the argument?
I think that the argument or the reason for selecting those substances is that they were working under better conditions, less cost, but for the company and for the refrigerator, but the environmental cost was very high. Then our point was, if you need to assess the suitability of a new substance, you need not only to consider one property, the property which is of interest for your company, you need to also consider some other dimensions. And we developed a mathematical method to try to take into account all different conditions.
But what are the conditions you need to take into account when we talk about such things as environment? Because it seems to be so diverse. Like it could be, I don't know, depleting ozone layer, but it could be good for the fishes, I don't know, and vice versa. So how do you do that?
Difficult. That there is no way to solve that.
I can give you an example. It's just this puzzles me. It's Christmas season, and every so when I just moved to Germany, I saw in Leipzig on the main square a live big Christmas tree. And back in Russia, they use plastic Christmas trees that they assemble and then disassemble.
In Colombia too.
Yeah. And so I got confused because I thought that Germany is a green country and environmentally friendly, but they caught an actual tree. But then I thought about it a bit more and I'm like, okay, how much plastic do I need to produce a plastic tree? Yep. And like how much carbon I take from the atmosphere for growing an actual tree. So those things are
Yeah.
quite tricky.
And there is a name for that. It's called life cycle assessment.
Okay.
You need to consider is when you cut the tree, the actual tree, when you cut it, what is the environmental cost? What happened? How much time do you need to get another tree of that sort? When 25th December, what do you, or no, when we get rid of the trees in the 1st of January or something like that, 10th of January, what happened with that tree? Is going to pollute something or not? And I think if we run the life cycle assessment of those living trees which have been cut, then I think it's better than having a plastic tree, because the plastic tree is going to end up in some years.
Landfill, for sure. Yeah, okay.
Yeah, then you need to consider those things, yeah.
So and coming back to so I gave it as an example of how you can assess any environmental problem from this chemical point of view. So what are the factors that people usually have to take into account, like other than this life cycle?
Normally are, for example, in terms of environment, ozone depletion potential, global warming potential, but those are numbers. I think we need to move in another direction, and is something like a network of consequences. I think we are accustomed to deal with numbers, but perhaps it's better to go in the consequences of those.
So are you a mathematician? Are you
no. But I very surrounded of mathematicians, and
because you say that you don't want to deal with numbers, so I started to suspect something. Okay.
No, but I think is not that simple as converging the complex dimensionality of a problem to 3 numbers or something like that. You need to explore the interactions of what you are doing, and that I think that's the way to go.
There is another space in this kind of related to this direction, is the idea of closed ecosystems. Like, how do you model an ecosystem where certain species can live only using, I don't know, external energy, for example, like sunlight or something. There were even some experiments done on this. Like, I know that at some point in in Krasnoyarsk, I think I visited them. There was this place, it was the project called Bunker 4 or something. In the 80s, Soviet Union was almost dead, and still they were running this crazy experiments of how much time a single person can live in a closed bunker in this closed
I remember
ecosystem.
That, yeah.
And there was this guy that I even almost so I agreed to have his former colleague to contact us for the podcast, but he passed away, unfortunately. Engineer Bugreev, who spent, I think, a year and a half alone in a closed ecosystem that was powered by algae. And I mean, it's kind of both tragic and funny at the same time. But I do think that it's a very, very interesting direction that people pursued during the Cold War because of marketing reasons, I guess. I don't know how to explain it else, but it's an interesting idea because, of course, if you can build closed ecosystems, then you can colonize space. If you don't build closed ecosystems, you cannot, right? Because in the end of the day, you have a very limited space and a very limited amount of mass that you can send to space. So when we wouldn't like models developed for this kind of thing help ecologic questions as well, because it feels like it's kind of easier to model closed ecosystem with limited number of species, and then the mathematics that you develop there might be usable for the whole planet, right? But do people do something in this direction, or is it not?
I think, but of course, at the level of the planet, the ecosystem is very huge, then you have by far more complexity. But yeah, there are many people working in that direction. Perhaps they are, I don't know. I think what you need to go in the right direction is having people from different disciplines working in there. Because for example, as a mathematician, you may think in the interactions, but you don't know which are the actual important interactions. Then perhaps you need an ecologist or a biologist or something like that.
Okay.
And that's the kind of thing you need, and also the models. Yeah.
But even chemistry-wise, right? You probably, as you mentioned, we have certain chemistry that's biased, and we might have some very useful substances that we just don't know of. And the usability of these substances, there's no usability for it, let's say, in this situation when you have an open ecosystem, but they might be usable in a closed space. So in order to do that, we also need to probably design this kind of space and work within it. Is there any other way? Like, can you simulate this kind of things? Do people do something in this direction? Or
No idea. No, I don't have something here in that direction. No.
But because it's fascinating, like I've been like there are two things that I don't understand about space, literally, and what one of them is why don't we try to have closed ecosystem, and the second is why don't we try to send life to other planets, not human life but just some life. Like, but this is an ethical question, I guess. Like can we do it? But I feel it's interesting that people don't even talk about it.
Yeah,
because we know that there are some planets where our life can live. And we don't have any sources and any information whether there is life there or not, but we can find out as long as we send some spaceship there. So why don't we send some bacteria somewhere and then check, and if there's no bacteria, why don't we just send them there?
Yeah, that sounds appealing. Yeah.
Yeah, I don't know, but this seems to be out of the discussion. The whole people seem to be focused very much on the planet only.
Yeah, indeed. Yeah.
Okay, so I suggest we wrap it up. I think it was nice. Thank you very much. It was I don't know if you want to suggest something in the end for the people who are interested in what we discussed, maybe a book to read or a course to check out if people are interested in mathematical chemistry.
I think,
Where should people go?
No, I think, for example, in mathematical chemistry, what I think is important, or what I've learned with the research I've done, is that it's important to not only to consider, for example, the connection between mathematics and chemistry, but also the social background. When you start to understand that, then you start to see why some things are done in the way they
How do you mean? Can you give an example? Chemistry is very... You said it already. You said chemistry is very social.
Oh, yeah, it's very social. Very social. For example, we recently published a paper. It was accepted. It's not yet published. But we found that, for example, when Donald Trump said that there were two substances that were antimalaric substances. And he said, this is the best medicine against COVID.
Okay.
Then the amount of even scientific publications in that direction skyrocketed after those tweets. It's social.
Okay, yeah. Ivermectin or something.
Yeah, I don't remember.
No, but the ivermectin is something against worms. That's dewormer.
Yeah, but and there are records of that. I found the number of
But this
papers.
is also contributing to the same idea of bias, right? So and that's actually an interesting thing that I forgot to ask. But like, if it seems that diversifying the background of people in the field might also change the bias in the field.
Yeah.
Or diversifying the educational background of people, in a sense that do we have such, like, for example, when I visited China, I was amazed with the fact that the traditional medicine and Western medicine are in the same drugstore. It's like you go to the drugstore.
Your decision, yeah.
There is aspirin and there is the frog. You can choose. It's fine. Both cost comparable number of money. And I was very surprised because in some sense it's like the attempt to save this line of work and try to develop it further using the methods that were developed there. I'm not sure about the efficacy of those methods, but still, the point is that it's kind of a way to preserve a different bias that might be potentially useful for example, chemical space exploration. So are there attempts in this direction? Do people try? I don't know. Do people? Okay, so I don't have a soul. So for me, of course, the natural idea is like, let's teach two classes, two different chemistries, and see whether they...
No, yeah. I've read papers using different methodologies, different approaches to science, and some of them with some more social content and some others with more scientific content, and then you see differences. Yeah.
No, but I mean on the level of education system, like we teach the same chemistry to people or not? Is it like globally?
Yeah, but it's also important. Yeah, you teach the same, but it's how to teach that. If you, for example, if you tell why those things are important or what kind of reasons led to those situations, for example, why I don't know why in chemistry in the 1950s we replaced making chemical reactions to come up with the molecular structure of a substance, and we start to use machines. We start to use spectrometers. Why?
Because we got them.
But why? And it was because of the war.
Okay.
But you need to tell that, because then you start to believe that things are coming. But if you don't see why, then you don't understand the processes of science. And I think that's important. And even for popularization of science, you need to tell those stories. To try to understand the process. And I think that's also what is happening with all these anti-vaccine things, that they don't understand the social process of science.
Yeah, well, that's true. Most of the people don't. But even scientists don't. I mean, to the credit of people, I have to say that there are a lot of scientists who just think that the science is when they just do what they want to do using the money of the taxpayers.
Yeah.
So it's
that's what I say, that is important to know the social background.
Well, one of the examples, by the way, that I came across at some point is the difference between the paintings of during the Renaissance, or like after the Renaissance, the paintings of Dutch painters and Italian painters.
Mm-hmm.
And I was like, they have very distinctive styles, and Dutch painters mostly paint some local life of people, dark rooms, not a lot of light, a lot of brown and black and so on. And then in Italy, it's all fine and dandy, usually some religious story with a lot of light and green and blue and yellow and stuff. And then I came across some research that was basically telling that the price of pigments was structured in such a way that in the territory of modern Netherlands, the pigments were super expensive, and the affordable pigments were basically from this spectrum of black and brown and so on. And so people kind of like, okay, what can I draw with that? I clearly cannot draw the jovial scenery of Jesus coming back from the dead. So I'll just draw how one guy steals a coin from another guy in a tavern,
And the same happens in science.
And it's also kind of a chemistry thing too, right? Because it was just some people could produce certain pigments and some couldn't.
Yeah, and something is happening. Similar things are happening now with the work in Russia and Ukraine. Is that, for example, the helium supply is going down because of the war. Then we don't do a lot of chemistry with helium, but helium is used for several chemical processes for having non-reactive atmospheres. You need sometimes that, and then you need to switch to shift the approach to your experimental research because of a war. There are clear evidences of the effect of wars in the kind of research we do.
So what are other social huge social factors that affect the research direction? So wars is something that you mentioned, politics in the sense of
pandemics too. Pandemics.
With pandemics, I think everybody saw that my favorite part is that Bill Gates was saying, we're going to have more pandemics for 10 years. And then once we got a pandemic, everybody's like, oh, he knew, blame him. It's his fault. It's like, no, guys, it's not. It's like, if somebody tells you, hey, it's slippery down there, and you go and you fall, it's not because he made it slippery. He just saw that it's slippery and he wanted to warn you this is a different thing. Yeah. So what else? Okay, so pandemics, so some global wars.
Political systems too.
Okay. So is there a difference between democracies and dictatorships?
That had something that a colleague of mine...
I would expect the dictatorships do more drugs.
Yeah, perhaps.
There is this wonderful book about drugs in the Third Reich. There's this guy who basically advocates the case that a lot of leaders of the Third Reich were just basically on speed all the time.
Yeah.
And it explains a lot about so okay.
Yeah, I think that has to do with the.
I'm sure now somewhere in Moscow they man, I'm sure some very heavy stuff.
No, but I think
developed
the political systems has to do with the kind of, for example, think on scientific meetings or something like that. Or in former times with the Iron Curtain, for example, it was difficult, the interchange between the two parts of the world. There are parallel discoveries that now we are realizing that they were happening. And I think that's another case of those things, political, and also the kind of things, the kind of starting materials you can buy. For example, what I mentioned about helium, that has to do with things like that. Or for example, when in one of the world wars, Germany was not ready to have oil, I think benzene. They didn't have benzene, and then they said, okay, then let's start to synthesize it. You need, those things change the way of doing science too, because you have bans. So, for example, another thing is the environmental concerns. That's another social is motivated by the scientific output, but the coming back is a ban. For example, with the problem of the refrigerants, they said, okay, don't work anymore with these substances, try to find a replacement. Or for example, with chemical weapons, if someone discover a new chemical weapon, then they say, okay, stop working in this direction. Those are things that are related to that.
Yeah. Also, I also remember that there was this the pigment story, for example, that the fact that the genes are blue is just that it happened that that was the cheapest pigment in the US when the genes were designed, and now it's like the way how society behaves and things. This is the standard, so this happens in both directions, and
exactly.
It's not very obvious. I have a friend. He has a theory that he's in Kiev now. By the way, Grisha. I hope it's gonna be fine. And he has this theory that he tried to analyze how inventions happen and when something similar was described in the literature. And he claims that there is like an average 20 to 30 years difference between some sci-fi mentions some invention and something occurs in reality. And his claim is that basically some kids or teenagers read stuff and science fiction and they're like, oh, that would be nice to have. And then they think about this in a more kind of systematic terms. They have also more time and they can kind of control and steward their career. So some of them might actually invent something, maybe not necessarily exactly how it was described in the literature, but something similar to how sci-fi people envisioned it.
Yeah, so and you have something like the cycle there. That's the feedback. Cycle.
All right. Now I think we're done. It was nice.
Okay. Thank you for the invitation.
It was quite cool. Thanks a lot. Take care, guys. If you're watching us, you can subscribe. You can also say that you like what you saw, or you say that you didn't like what you saw, in which case we will find you because we have a very special set of skills. Thank you very much and see you around. Hopefully it was interesting.